ideas. We are basically coming from a different end from integrated optics and are trying to use optical principles also for computing applications. And what we basically do is we build systems on chip that are based on optical waveguides for guiding light signals across the chip and manipulate those with active components to implement some information processing capability. And some of those actually translate quite nicely into the optics domains, such as multiplications or additions. And then we combine them into larger structures to eventually arrive at a brain-inspired platform. So it's an analog computing approach, but comes with the benefits of optics. And those are essentially that it's a low power system and high throughput, and this gives some advantages if it's scaled up to larger sizes. Yeah, so we are a somewhat applied physics group, and therefore design our own circuits. We built those basically in-house up to now in Münster, but following now in Heidelberg as well. And these are typical chips that look like something on the left-hand side here. So these are waveguide structures. All the pink lines are essentially light rails that guide optical signals across a chip surface. And we equip those with functional elements such as detectors, laser systems, and so forth. And then embed this optical framework into a first analog digital framework, analog electronic framework, and wrap a digital electronic framework around that to interface that with more traditional hardware. A lot of the work is actually chip design in the lab and nano fabrication. So we do that with our own tools, write it with the e-beam, dry etch it into silicon photonics materials, such as pure silicon or silicon nitride, and then measure them with methods from integrated optics. So this turns out quite nicely. It doesn't need as many fabrication steps as with CMOS devices, but much fewer, and therefore it's also can be handled in a university setting. And here's an SEM picture of a typical of these chips. They're usually somewhat 2 by 2 centimeters in size and have these lines here as designed that we use for guiding light into and out of the chip for our measurements. Okay, a drawback of this approach is that the materials are mostly passive, and for any sort of learning application, we want reprogrammability. So this has to come later on top. And for that, we equip these silicon chips with more active materials. And one that we particularly like, especially for reconfiguring, is a so-called phase change material. You all know this. This is essentially the stuff that is on rewritable DVDs or has been used there, where essentially the material is used to change the reflectivity if it goes a crystalline phase transition on the nanoscale. So this is a ternary alloy. It's called GST. And comes in various mixtures. We use one from a commercial target with a 2.5 stoichiometry. And this is interesting from an optical point of view because it has very different properties if you go between these two different crystal states. So it can either be sort of a glass-like structure that is amorphous, or it can come as a crystal, and then it behaves much more like a metal. Hence also the change in the optical properties. For photonics, this is interesting because the transition is reversible, so you can go back and forth many times, which is also why it's interesting for DVDs. And you can switch that on very short timescales, so typical are sub-nanosecond switching times, but it can also lie in the femtosecond region if one really pushes the boundaries. And then by using suitable pulses, you can go back and forth many times and hence have therefore a programming capability that can be transferred directly onto these integrated systems. It's also visible directly by the naked eye. So here's some work from our collaborators in Oxford, where we essentially get this material from. So this is a sandwich of this active material between two electrodes. And now if you go between these phase transitions, you can see here with the naked eye that the color changes dramatically if the crystal stage is changed. So basically in this particular device, which is the same film, but in two phases, it can either be brown or blue, or you can also go to different colors and hence have a nice platform also for building displays essentially. Important for us, you don't have to do this for the entire film, but it can also work with very small crystal domains and is therefore directly compatible with these sort of waveguides devices that we built. And hence what we do is we take this large film and put it directly on top of the surface. So the waveguides that I showed you earlier, and then we decorate them with a little patch of this GST here on top, which functions as a programmable element, or yeah, in a sense, an optical attenuator that can also be interpreted in terms of neuromorphic function. And this way you have a very basic version of an optical memory on a chip. So essentially what it modifies is the transmission through the device. If it's a metal, it's very absorptive, and hence high intensity pulse comes out as an attenuated pulse. If it's switched into the amorphous or the glass-like structure, then it's more transparent and you don't get so much attenuation. And then what we measure is essentially the power that comes out at the output, which also encodes the information in this system. Here's how it looks in real time, not as nice as in the rendering, but you can see that it's a very thin film, typically 10 nanometers, that is capped with some preventive oxide for retaining the crystal state. Okay, the way it works is actually quite straightforward. So if we assume that we have this glass-like structure and we send in a read pulse, then it's not attenuated and measured over time. You basically get out what you put in. If it's in the crystal state, you send in the same read pulse, but you get a lower pulse out. So you measure the difference between these two signals and can basically work with the optical contrast that contains the memory. And in principle, all crystal states in between are also accessible. Hence, it's an analog processing platform. For programming it, you need a somewhat higher intensity. So this is done with a stronger write pulse at whatever wavelength. This basically melts the material, so the atoms are in a disordered state. And if the power is taken off very quickly, it is melt quenched. So the power dissipates into the surface here, and the atoms don't have time to reorder, so they form this glass-like structure. To go back, this has to be done some more smoothly. So we add a little shoulder to this initial pulse, which basically keeps the temperature at an elevated point, and hence the atoms start to wiggle again, but they are now kept warm and have time to reorder. So this way, the material can be reprogrammed to the crystal state. And this is repeatable. So by basically playing with the shape and the intensity of the pulse, you can go back and forth and implement the structure. It's also directly visible on the atomic level. So if you take a cut through the waveguide here, there is the sandwich of the light rail, the capping layer, and the active stuff in between. In the amorphous state, there's no order, so a Fourier transform just gives this centrosymmetric halo and no crystal structure that you would expect. If it's crystalline, you can see that there are some little microcrystallines forming inside the film. So it's not single crystal, but polycrystal. And this, again, Fourier transform formed reproduces the stoichiometry of the target that we purchased commercially. So this is essentially our platform. It's just a waveguide with some active stuff on top, but we can use this for building some functional devices, such as very simple neurons that we can use for implementing MAC operations on such a chip system. So the idea is essentially that we duplicate this light rail structure and then sum all of them in one device. So this way we can basically perform weighting and addition function in a device, and then also exploit the nonlinearity of the photonic platform to basically do some functional work on the result. And this way works by using multiple waveguides that are each equipped with one of these programmable elements. With that, we modulate the intensity that is going forward later on into the device. So all of these light rails are inputs. They are summed up by operating on different wavelengths. And then we take the entire power that is guided inside the waveguide and perform a measuring operation to determine whether this perceptron is actually firing. Or translated into the optics domain, it would look like this. So we have, for example, 4 inputs. Each of them carries a different color so that we don't have interference later in the waveguide. These inputs are weighted. So they each have this little patch of phase change material sitting on top. Therefore, we can turn some of these inputs off or blank them out or use any level in between. Then we use a wavelength division multiplexer to combine all of these 4 elements onto one common waveguide. So this one is then actually carrying the scalar product of the weights times the input intensity. And this we use for tuning this nonlinear element, which is actually a resonator here. And then we measure light that is propagating past the output. So essentially, this way you have a very basic artificial neuron that works all in the optical domain because the programming is done optically, but also the input and hence the inference action. Then by using this layout tool that I showed you earlier, we can scale this up and build some circuit devices. This is also what we did. So a very basic 4-neuron system is the following here, where we basically wanted to do some classification of basic letters. So it was a 4-neuron element that has exactly these systems from before. So there's the nonlinear resonator here for providing the spiking action if it's driven by a short pulse. And then the input is the multiplexer plus these 4 waveguides. The multiplexer is always combined of 2 rings here, which transfer light from the input into an output here. And by changing the size of the ring, you can basically pick different colors that are co-propagating on the input waveguide and join them again in the backward propagating direction on this common waveguide. Then the phase change material is sitting in between here. So each of these short vertical waveguides has a little patch. This one is actually programmed to turn some of the pixels in on or off. So basically all the black ones are turned off, the white ones are kept on, and hence we have 15 pixels to play with to basically represent letters in this architecture. And because they are different enough, the neurons are actually able to differentiate between these 4 input patterns as a proof of concept. Okay, so what this thing actually does is it takes some input state on 15 different colors, and it multiplies it by basically a 15 by 4 matrix. So 15 weights on 4 neurons. It uses then the output to select whether these neurons should fire or not. So this is basically rectification, and hence also the interesting steps for CNNs if they were translated into the optical domain. And actually, the benefit comes from the fact that this matrix vector multiplication is done in a single time step. So all the inputs propagate through the same system. They're measured all in the same time, so there's no sequential operation. But basically, it only takes one frequency cycle of such a system that does the entire classification. So this multiplication works as the following. Basically, we have 2 numbers that we want to multiply together in the optical domain, and we use 2 ways of representing these numbers. The first one is basically the amplitude of a particular light field. So this is our number A. Then the second one is attenuation or transmission, input differently. So this would be the phase change material sitting on top of the waveguide. And if we measure the output power that is coming out on the other side, we basically directly get the analog product of the amplitude times the transmission, but get it at a measurement frequency that is determined entirely by the optical device. So typical rates are in the multi-gigahertz ranges. The amplitude has very high dynamic range, so there's a large number scale that can be worked with. And of course, the power measurement can be done at the response time of photodiodes, which is quickly. What is also interesting and differentiates this platform from electronics is that we have the possibility to recycle a waveguide and not use just one color, but multiple colors. So basically, if this works on one color, it also does so on many at the same time. And hence, you can scale the throughput or performance of the system also in the spectral domain. All of this propagates through the same system, but it performs different multiplications on different input vectors, yet with the same weight, of course. If this is translated again into a chip, it looks also much more to a much closer to a matrix multiplier. So in this case, we got away from these ring resonators and rather use these short bands here. They do more or less the same thing. They transfer light from a horizontal waveguide into a vertical one, and you can encode the weight here on this little band, similar to these ring structures. But now we can arrange that also in a much more mathematical mapping. So basically align the neurons in the horizontal direction and the pixels in the vertical direction. And then you already arrive at a matrix representation that is encoded now in these phase change materials. The many wavelengths you can also generate nicely on chip using, for example, a frequency comb device. So this is a little ring resonator that is nonlinear and generates a spectrum of evenly spaced colors here. Then we can take these colors apart, modulate each one with an electro-optical device, and therefore encode the numbers or the vectors that are going into the matrix. And then by picking sets corresponding to the number of rows that we have in the matrix, you can basically extend this in the frequency domain and use multiple vectors at the same time. So therefore parallelize the operation also in this respect. The comb we don't build ourselves, but we rather get it from EPFL. So Tobias Kippenberg's group does that. So you can see such a spectrum of a frequency comb. There are many, many lines to work with. And in principle, they all propagate through the same matrix. Out of those, we only pick a small number since we don't have so many modulators in the lab. We also make the matrix smaller so that we can handle it. So it's in the end, it's a 4x4 matrix, which you see here. On each intersection here is again the phase change material. We use some special fiber to chip couplers so that we have the broad bandwidth that we want, and then put the frequency comb in front of that. And then you still get many lines, about 200 or so. Out of those, we then pick 16 to match 4 inputs on 4 different colors, therefore have some way of pushing several devices, several vectors through the same device. A typical setup is something like this here. So this doesn't look as organized as an electronic lab. Here in the front, you have the frequency comb. The heart of the comb is a little chip that is sitting here in the center. The rest is amplifiers, phase locking equipment, and driving electronics. But what you get is a spectral comb that is coming out here at the fiber. So this we can take and then go through commercial wavelength division multiplexers. So that way we can basically select some of these wavelengths of interest. They are then sent through electro-optical modulators that are also free space, and eventually they go into the chip that is sitting behind this. At the output, we pick up the signals again, go to these photodetectors here, and then measure the analog output from the matrix vector multiplication, digitize it, and use that then further with an FPGA for data analysis. With such a small matrix, you can, of course, only do some things. So use that, for example, to work on digit recognition. So this is can be mapped at least to such a system. where we basically work with 4 different kernels here in parallel, map them each onto a different set of 4 wavelengths, and therefore take out the convolution step out of such a small scale CNN. The rest is done electronically and use that for identification. So this works actually also quite nicely as expected. But the interesting bit is essentially that the throughput is very high. So the system can operate at the bandwidth of the photodetector, which in that case is about 14 gigahertz. And each clock cycle is basically 1 full step of the computation that translates also into some teramag operations per second, even for this very small system. Okay, so what is next is, of course, to scale this. On the university level, it's hard to go to larger matrices, but on a commercial level, it's much more doable. So we're basically translating that to a silicon photonics platform where you don't only have these passive elements, but also the actives. So they're coming with photodetectors in the end. They're also coming with the multiplexers directly at the input and the modulators. And this way, all that is needed is basically a light source. On the optical side, of course, it needs to still be embedded in an electronic framework so that you can actually interface it with a normal computing environment. So that requires AD and DA converters that run efficiently and also fast. And with that, then you can basically do the more interesting things that are not just limited to these smaller matrix sizes. But this is basically what I wanted to say. So I have to thank some funders and especially our collaborators at Oxford, where we get the phase change materials. We have theory support from Exeter University. David Wright is the lead here. The comb sizes come from EPFL and also some ideas for further scaling. And a lot of the algorithms and the platform theory is done together with IBM also in respect to scaling. And with that, I'm done and will be happy to take questions. Thank you.